Welcome back to part 2 of chapter 3, where we are looking at how to describe data. So far, we've talked about the measures of center. We've talked about the measures of dispersion. We've also talked about the measures of shape. And right now, we are looking at a concept of the distributions of the data. So in the last video, we talked about that 68% of our data falls within one standard deviation from the mean. Now, looking at this distribution, we can see I labeled the mean as 0. This distribution is what we known as the standard normal distribution. And I will explain all this. So we have the normal distribution and we have a standard normal distribution. In a standard normal distribution, we say that the mean is 0 and the standard deviation is 1. So we represent a normal distribution as mu, sigma. So where mu is the mean and sigma is the standard deviation. Now in this case here, we have a mean of 0 and the standard deviation of 1. So this is known as our standard normal distribution. Okay. Now in our standard normal distribution, the horizontal axis is known as the z-axis. So this is also known as a z distribution. Now what is z? Now the z or the z values, or also called the z-score, tells us how many standard deviation our data value is away from the mean. So we can use the z-score to determine the number of standard deviation a data value is away from the mean. So that's the z-score. Now, so today we're going to look at how to find the z-score, percentiles, quartiles, and comparing standard deviation. That's going to be the focus of this video. And with that, we would be coming towards the end of chapter 3. Awesome, let's get started. So how do we compute the z-score? Now to do that, let's look at a different example. So let's look at this example that we had here. So we had these numbers 20, 31, 50, 69, and 80. Twenty, 31, 50, 69, and 80. So looking at those set of numbers, we had that the mean so x value was 20. You write it. It's 1, 50, 69. Okay. And what was our mean? So the mean was 50. Okay. So x bar was equals to 50. So this is, so if I am to draw a distribution out of this, so we say that this is x and the mean here is 50. This is our normal distribution. Now, of course, this distribution, the distribution of this data might not look like this, meaning that it might not be symmetrical. It might be approximately symmetrical, but I just want to put it the context of the mean here in the context of this distribution. Now, what we are going to do is transform this normal distribution, and I'll call it ND, to a standard normal distribution, SND, standard normal distribution, in which, in this distribution, the center is 0. So we can have so many types of this normal distributions, and we can always transform it to a standard normal distribution in which the mean is 0 and the standard deviation is 1. By doing that, so take for example, the example of class 1 and class 2, we would have two different types of distribution. But when we normalize both of them, we have the same type of distribution, just one, which is the standard normal distribution. Now with that, we can use this to compute the things like the area under the distribution, the probabilities, which we will see in a future chapter. All right. So how do we transform this from this x to z? So the transformation is this. So z is equals to the value of our x minus the mean. Now x minus the mean divided by what? Divided by the standard deviation, sigma. Now, if we are looking at a population data, so this will be the z-score for population. What about sample? If we're looking at our sample data, then the z-score is equals to x minus x bar divided by the standard deviation, which is s. So that will give us the z. Now, in this case, if I ask the question, how many standard deviation is the score 69 from the mean? So we know that the mean is 50, and we want to know how many standard deviation is 69 away from the mean. Now, if you recall, for these set of numbers, we found the mean, the standard deviation to be 25.1. So one standard deviation was 25.1. Okay. Now, so we have S is 25.1. That is a sample standard deviation for these data sets. So our Z for 69 will be equals to 69 minus the mean, which is 50. So X bar, the mean is 50, divided by the standard deviation, which is 25.1. So this would give us how many standard deviation our data is from the mean. And 69 minus 50, that is 19, divided by 25.1. So everybody pick out your calculator and perform this computation. So we have 19 divided by 25.1. And this gives us 0.75697. So round to two decimal places, 0.76. So what that means is that 69 is about 0.76 standard deviation away from the mean. So that's the interpretation of that. And of course, we expect it to be positive because 69 is greater than the mean of 50. So if we are to find for 31, we expect to have a negative value in this case because it will be less than 0 in this case. And let's look at let's find the z for 31. So that will be z will be equals to 31 minus 50, which is the mean, divided by the standard deviation, which is 25.1. And in this case again, so we perform the computation, 31 minus 50, which is minus negative 20, divided by 25.1, which gives us is approximately negative 0.79 797, I was just saying negative 0.80. Okay, so it's approximately negative 0.80 somewhere around here as well, to the left of 0. So we assume that this is negative 0.8. Okay, so that's how to find the z-score. So the z-score measures the number of standard deviation a data value is away from the mean. That's a z-score. Good. Now, if you have any question, let me know. So let's look at something very interesting, which we call the measures of relative standing. So in this case, we're going to be comparing the measures between or within data sets. What does that mean? And we're going to use the z-score for making this computation. So by measures of relative standing, we are trying to look at how compared to population, for example. So let's assume that I am the president of Nigeria. And there are other presidents of Nigeria, and we want to compare my height with the height of, say, President Obama. And of course, what we are trying to look here is, am I taller than President Obama relative to our population? So the population of the US presidents and the population of Nigerian presidents, we want to compare if my height is more than that of Obama. So that's what we're going to look at here. So we are going to be comparing the variation between two different sample or population. So let's compare the height of two people. Okay, so let's say Italma's height is about 17 inches. And the mean height of all presidents in Nigeria so the mean height of all Nigeria presidents is 71.5 inches. So what that means is that we look at all Nigerian presidents in history and find the mean height, and that's 71.5. So we can clearly say that I am taller than the average height of all presidents in Nigeria. That's what how we can describe this. Now, let's also assume that the standard deviation is about 2.1 inches. Okay. Now the question is, how far away is Italma from the average height of all presidents? So let's ask that first question. How far am I from the height of all presidents in Nigeria? So that's what we just did above. We find the z-score, because the z-score tells us how many standard deviation a data value is away from the mean. So to solve this, so the question is, how far away is Italma from the average height of all Nigeria presidents. So that is, again, Z is equals to X minus mu divided by sigma. So we're dealing with the whole population here. And so this standard deviation is sigma. And this mean is mu. So we have mu is equal to 71.5 and sigma is equals to 2.1. And now our Z will be 76 minus 71.5 divided by 2.1. Okay? And when we solve for that, so 76 minus 71.5 is equals to 4.5 divided by 2.1. Again, pick out your calculator. And I'm doing this, I'm demonstrating this so you can walk along with me. 4.5 divided by 2.1, that gives us about 2.142857 and so on. Now, I will tell you how many decimal places to round to. So if I tell you to round to 2 decimal places, so that would be approximately 2.14. So what that means is that I am 2.14 standard deviation away from the average height of all Nigerian presidents. Sweet. Which means that am I usual or unusual? So we said in the previous video that 95% of our data lies within 2 standard deviation from the mean. And that which we classify as usual is within 2 standard deviation from the mean. I think that's what we said in the previous video. Yes. So it's 95% of our data is will fall within 2 standard deviation from the mean. Now, on any data point outside 2 standard deviation from the mean, we classify it as unusual. So relative to my own population, I am actually unusual. So which means that I'm actually very tall in that sense relative to my own population or to the population of presidents in Nigeria. All right, so let's look at so that is for Italma's height. So let's look at Obama. Now, President Obama's height is, say, I can ask Alexa to tell me, but let me put it obviously around 86 inches. So clearly you can see that Obama is taller than me, 86 inches. I'm 76 inches, way taller. However, that's not the question. The question is who is taller in terms of the 2 population. So in the context of the 2 sample of data, presidents in Nigeria and presidents in the US. So is Italma's height taller than that of Obama's height based on their populations? So that's really the question. So who is relatively taller is what we're asking. So let's look at the mean. So the mean for all presidents in the US let's say is 80 with a standard deviation sigma is equals to 3.30. Now, what is Obama's height? How far is Obama away from the average height of all US presidents? So Obama's Z-score will be equals to 86 minus 80 divided by 3.30. Now, if you do that, you have 6 divided by 3.30, and this will be approximately what? Bring out your calculator. 6 divided by 3.3 gives us 1.818181, keeps repeating itself. So approximately 1.82. So now the question is, who is relatively taller? So the question is, who is relatively taller? As you can see, Obama is kind of usual in terms of relative to the height of all presidents in the US. It's not more than 2 standard deviations from the mean height of all presidents in the US. So it's considered usual. It's not unusual to have a president of that height. Whereas in Nigeria, it's unusual to have a president of my height. Now, who is relatively taller? To answer that, you use the z-score for the population. So we use the z-score for the population. We compare these two z-score. And so by comparing these, you can see that I am relatively taller than President Obama. Yay! All right. So this is, remember, this distribution for the empirical rule. And so let's say this is 0, 1, 2, 3 standard deviation, -1, -2, -3. So we said within 2 standard deviation is what we classify as usual. Within 2 standard deviation. Otherwise, this is unusual. Unusual. Something unusual. Oh, I need to get an iPad. Writing on the screen can be very interesting, but it's fun. Unusual. Finally. So usual, we say it's likely. Unusual, we could say it's unlikely as well. So a score is this score between -2, this is -2, and +2 is considered usual or likely. And the z-score more than 2 standard deviation from the mean is considered unlikely or unusual. And we will use this also to determine if our hypothesis is true or false when we get towards the last one of the second to the last chapter. I think that's on chapter 9 on hypothesis testing. So we are building up on a story that will lead us to making the right form of decision. So what we've looked at here is how to determine the z-score, how to also determine the measures of relative standing. Okay, so now you know how to compute the z-score. Awesome. Now let's move on to the next topic, quartiles. What are quartiles? So what are quartiles? All right, for this, I'm getting the paper. So a quartile, we think about 4, right? Number 4. So there are 4 parts. Now, if there are 4 parts, how many quartiles are there? So let's assume this is our book, and I want to determine the quartiles in our book. So if I divide this into 2, oops, that was really bad. Now, this middle point is the median. Okay, that's the median. We said the median is the middle point of the data. So we just cut this data. This is our first cut. Now I take the data to the left. I also divide it by 2. And I yank it as well. Ooh. My second cut. Now, this middle is called the first quartile. And then I take the data to the right. I divide it into 2. And have another cut. Ooh. And this midpoint is called the third quartile. How many cuts did we just do? We had 3 cuts. The first cut gave us the median. The second cut to the left gave us the first quartile. And the third cut to the right gave us the third quartile. The median is also known as the second quartile. So looking at it, we have how many pieces of paper? 1, 2, 3, 4. We have 4 parts, but we have 3 quartiles. All right. I hope that was helpful. All right. So there are 3 quartiles, but there are 4 parts. So the first quartile also known as Q1, is the, bring back my paper. When we divided it into 2, we have 50% of our data here, 50% of our data here. When I take the left-hand side and divide it into 2, we have 25%, we have 25%. So the first quartile, Q1, is the bottom 25% of sorted data. So that is the first quartile. The second quartile also known as Q2 in most softwares, is also known as the median. This is the median. And this is the bottom 50% of sorted data. All right. And then the third quartile, also known as Q3, is the bottom 75% of sorted data. Awesome. Cool. All right, let me give you some examples to make it much easier to comprehend. So let's say we have the set of numbers and we have to compute the quartiles of this set of numbers. 1, 3, 6, 10, 15, 21, 28, and 36. First, check if these numbers are sorted. As we can see, these numbers are sorted. Okay. Now we want to find the first quartile, the second quartile, and the third quartile. So first, let's find the middle. 1, 2, 3, 4, 5, 6, 7, 8. This is even. So we have that our first division will be somewhere around here. And then we take the second part divided by 2, somewhere around here. We take the next part divided by 2, somewhere around here. So in that case, our Q1 will be here, Q2 will be here, that's the median, Q1 and Q3. So how do we compute that? So Q2, which is the median, is equals to 10 plus 15 divided by 2, which is what? 25 divided by 2, that's 12.5. That is the median as well. What is Q1? Q1 is simply 3 plus 6 divided by 2. That is 7 divided by 2, right? No, that is 9 divided by 2. That is 4.5. And Q3 is equals to 21 plus 28 divided by 2. And by the way, there are different ways of computing quartiles, but this is the way I'm showing you because this is how it's explained in the textbook as well. So this would give us what? That will be 49 divided by 2, and that is 24.5. So that's how to find the quartiles, the first quartile, second quartile, and third quartile. And I will show you how to do this in Minitab as well in a different video. How to find the quartiles in Minitab. All right, let's look at a different example. So let's say we have another example. We have 1, 3, 6, 10, 15, 21, 28, 36, and now we're having an odd set of numbers. How do we solve for this? Again, we take our paper example, strike in the first, so the middle will be, this is 1, 2, 3, 4, 1, 2, 3, 4. So we know that from this, we can see clearly that Q2 is equals to 15, which is the median. Now, what is Q1? So when we look to the left side, we now have, so this is the middle here. So we look to the left. Now, some people will count from here, or some people just look at this. This is one, this is the next one, and the next middle will be this. And the next middle will be this to the right. So this will be Q2, Q1, and Q3. So what is going to be Q1? Q1 is equals to 3 plus 6 over 2, which is 4.5. Okay? And what is Q3? Q3 is equals to 28 plus 36 divided by 2, which is what? So that is 62 divided, no, it's 64 divided by 2, that is 32. So for some things, you don't need a calculator, so you can do this without a calculator. And of course, you can check this in with Minitab as well. So after watching the next video, which I'm going to prepare for your labs, you can now explore this in Minitab to verify that you have the same answer. So that Minitab would save you a lot of time, especially in your homework assignments and your exams. But it's also good to know how to solve these problems by hand as well. Next, let's look at percentiles. So what are percentiles? So a percentile is the value of the data at which X% of the data lies below that value. Now, what does percent do? So when we think about percentiles, we're looking at percent. So we have, in terms of quartiles, we had 4 parts. In terms of percentiles, we have we'll have 100 parts. But how many cuts would we have? We are going to have 99 cuts. So that means there are 99 percentiles as there are 3 quartiles. Okay, so what we are saying here in essence is that the 50, so I will say Q1 is equals to the 25th percentile. Q2, which is the median, is equals to the 50th percentile. And Q3 is equals to the 75th percentile. So when we computed Q1, we computed the 25th percentile, and so on and so forth. Now let's look at an example. So like I said, just like the quartiles, so the percentile is just like the quartiles, but separates the data into 100 parts as compared to just 4 parts. So that's the difference between a quartile and a percentile. Now, let's look at an example. But first, how do we compute the percentile? So let's say we want to find the percentiles of X. So this will be equals to the number of values less than X divided by the total number of values multiplied by 100. So let's look at an example. So let's say you scored 87 over 100 on a test. And 39 people scored lower than you. And there are 54 people in the class. Now my question for you is, what percentile is your score? What percentile is your score? So what we are saying is, what is the percentile of 87? So to compute this, we look at the number of values less than X, so less than me. So we have 39 people scored lower than I scored. So that will be 39 divided by the total number of values, which is 54, times 100. So we get our calculator and multiply 39, so divide 3900 divided by 54. So that gives us around, so let's do it again, 39 divided by 54. I mean, 39. Okay, so that's about 72.222. So approximately 72.222. So we say that that is approximately 72. So we can say that, so what percentile is your score? Your score is the 72nd percentile. 72nd percentile. So what we've just done here is that this score is P72. So that's the 72nd percentile. So I'm basically above the 50th percentile, you know. So my score is above average in general. That could be an interpretation. Okay. So next, let's look at one other aspect, which I'm keeping for the last part, which is outliers. How do we determine outliers in our data? So now we have all the ingredients in order to determine this. Now let's look at this set of data and determine if there are any outliers. So we have 1, 4, 5, 5, 7, 9, 12, 13, 13, 15, 21. Okay. Now, what we want to do is determine, is any of these numbers an outlier? Is 1 an outlier? Is 21 an outlier? And so on and so forth. How do we determine an outlier? So I'm sure by now you all have explored how to create what is called a box and whisker plot when we looked at in chapter 2. But in case you don't remember, a box and whisker plot looks something like this. Now, in a box and whisker plot, we have the minimum value somewhere here. We have the maximum value somewhere here. And then we have, let's say we have here, this is the median. This is the first quartile. And this is the third quartile. All right. Now, looking at this data set, so let's use this as a revision. What's the median? To find the median, you first have to check that this data is sorted. As we can see, this is sorted. How many data points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is even. So it's easy to find the median. So 1, 2, 3, 4, 5. So clearly our median is 9. So I can put here M is equals to 9. All right. And what's our first quartile? Q1. So we look at the numbers to the left, and we have the middle is this. So Q1 is equals to 5. What is Q3? We look at the numbers to the right, and we have Q3 is equals to 13. Okay? And then what's the minimum value? The minimum value is 1. The maximum value is 21. So those are the set of numbers that we can use, that we can discover from our box plots. All right. Now, how do we calculate, determine if there's an error, an outlier? So before we do that, I'm going to bring up one important information. So we found the mean is 9. I mean, the median is 9. Let's find the mean. What's the mean of these numbers? Let's use this as a revision. What's the mean? We have to add all of this first. So let's add it together. So we have 1 plus 4 plus 5 plus 5 plus 7 plus 9 plus 12 plus 13 plus 13 again plus 15 plus 21. That gives us 105 divided by 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is the sample size divided by 11. What do we get? We get something about 9.55. So pretty close to the mean, to the median. So this data is not so skewed as such. It kind of may have a normal distribution. It's pretty close. But as you can see here, the median, the mean is greater than the median. So if there was an outlier, then the outlier would be to the right, because the mean is affected by an outlier. But of course, this is very close. So it's most likely that none of these numbers are outliers, since the mean and the median are pretty close. But if there was a wide difference, then there's a likelihood of one of the numbers in the extreme being an outlier. But to find the outlier, we need to know what is called the IQR. So if our distribution is skewed, the measure of center will be the interquartile range. So IQR stands for interquartile range. If our data is symmetric, the measure of spread will be the standard deviation. So when you have a symmetrical data, the measure of center should be the mean, and the measure of spread should be the standard deviation. When you have a skewed data, the measure of center should be the median, and the measure of spread should be the interquartile range. Remember that. All right, and if you have any question, please don't fail to ask. So our IQR is simply equals to the third quartile minus the first quartile. So in our example here, that would be 13 minus 5. And what's that? So that's 8. So our interquartile range here is 8. So that's how to find the interquartile range. So the interquartile range represents the middle 50% of our data. So the middle 50% of our data. So this is 25, 75. When you subtract that, you have 50%. So the middle 50% of our data represents the interquartile range. Okay. Now to determine if there's an outlier to the left or to the right, there is this general expression that we will compute, which is Q1. So for the left, it's going to be Q1 minus 1.5 IQR. And for the right will be Q3 plus 1.5 IQR. So we multiply 1.5 with the IQR, subtract it from Q1 to determine the point at which any value less than that value is an outlier. And then for the right, it's going to be Q3 plus 1.5 IQR. Any value greater than that value is also considered an outlier. So let's compute 1.5 times IQR. So that would be 1.5 times 8. And if you use your calculator, you should have, so 1.5 is what? 3 over 2. So 2 goes in 8, 4, and that will be 3 times 4. That is 12. You see, you don't need a calculator. All right. So this will now be equals to what? This will be equals to Q1 is 5 minus 12. That gives us what? Negative 7. And in our data, we don't have any number that is less than negative 7. So there's no number towards the left as expected. Now towards the right, so we have Q3 is 13. 13 plus 12, that's 25. Well, as I also said, there's most likely there's no outlier in this data set because there's no number that is greater than 25. However, if you introduce a number, say 100 to the right, of course, the mean will be much greater because this is clearly an outlier. And then the median will still be closer to the previous median because the median is not affected by an outlier. So I will leave this for you to try yourself and then see if the 100 is an outlier. So you have to do this whole computation. By adding 100, you need to find the median, find the first quartile, find the third quartile. The minimum is 1, the maximum is 100 this time around. Determine the interquartile range and determine the threshold for an outlier. So that's how to detect outliers in a skewed data. Okay. And so with these, we've come to the end of chapter 3. In the next video, we'll be looking at probability.